Swayam Prabha. Digital India. Educated India.
Good morning. Once again, I welcome you to this course, online course, soil mechanics, and we are almost towards the end of this course. I have last topic which I have covered, completed, that is earth pressure, and now the last topic which I will be covering is stability of slope, and in the previous topic I have shown that to create different types of facility, sometime we have to retain the earth by using a retaining wall, and because of that, to design the retaining wall, how much is the pressure, etc., what are the different types of pressure we have discussed, and there we have also mentioned that we can, if you want to do some excavation, then we cannot do excavation up to infinite depth. In fact, if you go beyond certain depth, you need to provide a support, and then this different soil we can excavate up to different depth without support, and what could be the maximum depth of excavation without support, that we have discussed, and that was typically given in the form of formula, that is 4 C by gamma root K, and 4 C, where C is the cohesion of the soil, gamma is the unit weight of the soil, and K is the active earth pressure coefficient. And if it is a purely cohesive soil, then K become 1, the phi equal to 0, and in that case it become 4 C by gamma. So, that means if it is if soil has a cohesion of suppose 50 and unit weight of suppose 18 or suppose 20, then by and large we can suppose 4 C by gamma actually, when it is a purely cohesive. So, it will be 4 multiplied by C is 50 and this is 20. So, you can see nearly 10 meter depth we can cut vertically when it is a purely cohesive soil with cohesion value of 50. And obviously, if you want to excavate beyond that, then you need to provide support, or you have to make the excavation in a sloped manner, not vertical. So, similarly, if it is a soil of granular type, then this will be different obviously. In fact, granular soil we will not be able to excavate without any support. Immediately will cut and then it will try to collapse, it will collapse, soil will collapse, and it will finally make a slope, stable slope, and that slope angle generally close to the angle of internal friction or shearing resistance of the soil. So, that means we can provide a certain angle of slope to provide the stability. So, in fact, we have different facilities where we need slope. For example, if you want to make a long road, some places you need to excavate, some places you need to fill and make the embankment, and similarly, if you want to make a railway line, then similarly somewhere you may have to excavate or cut the soil or rock, or some places you may have to fill the earth to make an embankment. So, and when you make a cut or if you make an embankment, always we make in a sloped manner. That means, it will be, if this is the top surface of the desired road, then your you will make either this way, or if it is a excavation, then it will be like this and this. So, this is the angle at slope we have to maintain for the stability purpose of this entire structure. So, so that means here actually you have that slope stability analysis. That means, if you make a slope with 50 degrees angle, another slope you make with 15 degrees angle. So, whether both are stable, which one is more stable, all those things through proper analysis we have to find out. So, for this purpose let us that means slope stability analysis is one of the important topic in geotechnical engineering, and as an introduction I will just let you give this few lines. So, you can see that already we have discussed soil, and soil classification also I have mentioned, and under that is a gravel and sand, one type of soil which will be named as granular soil, and it has only a frictional component. That means, when you calculate the strength, then it has only tan phi, which gives you frictional strength. And potential slip surface, that means, if you make a slope with sand, then your slope will be granular material will be planar. That means, it will not be a curved. So, if there is a slope, that slope may fail like this, or it may fail like this. So, this is planar and this is a curved. So, granular soil failure plane will be generally planar, and it is relatively analysis relatively simple. And however, most soil which is not granular, that is cohesive soil, those type of soil will possess both cohesion component and friction component, and for that actually your will not be planar. So, a study of granular soil. So, but that means, we need to do both type of soil, slope with granular soil, slope with C phi soil, both we need to analyze. And but at the beginning, let us start with a granular soil as an introduction, and later on we will bring cohesive soil. So, which is simple, that is with phi. Let us take first, and you can see how the philosophy in slope stability analysis. You can see that this is a slope, suppose, and then that slope I can imagine a small mass of soil. So, this should be right angle actually. So, it is like that, and this mass I can consider the equilibrium. Then what are the forces acting on it? There will be a normal force, there will be a gravity force, and then it will try to, since it is a slope, it will try to move this way. So, there will be horizontal component in this direction, and this based on the equilibrium of this, if you draw a force polygon, it comes like this: W here, N is here, T is here, and based on this force polygon, what we can do, we can you can see we can, as I have mentioned, we have taken the element on the embankment, and W is the force at weight, and the force parallel to the slope will be W sin beta, which is shown as T, and force perpendicular to the slope will be W cos beta. That is angle, if the slope is, this angle is beta, then this slope, this component and this component, one is W sin beta, another is W cos beta. And for stability, sliding force must be equal to resisting force divided by factor of safety, okay, for stability. And if it is just verge of failure, that means F s will be equal 1. In that case, sliding force and resisting force, as long as they are equal, they are just stable, but if it is little disturbance, then the mass will start moving. So, because of that, for if you want, always we want actually a stable slope, and because of that, for stability requirement, the sliding force must be equal to resisting force divided by factor of safety. So, this should be small, and factor of safety always should be greater than 1. So, this should be smaller than the resisting force. So, if I take this definition of stability equation, then by providing this you get W sin beta equal to W cos beta tan phi, because this frictional force and because resisting force will be, this is the W cos beta is the force, frictional force N tan phi, actually N tan phi is the frictional resisting force. So, that is W cos beta was the normal force. So, multiplied by tan phi, that become your resisting force, and divided by F, and from here actually I can get factor of safety. Factor of safety will be tan phi by tan beta, tan phi divided by tan beta. So, this is the actually this is the very definition is this. If I keep F equal to 1, there is limiting condition, and then in that case that means phi equal to beta. So, that means at the beginning whatever I have mentioned, that if a sand, if I dump here by some means, if I dump it, this is a ground surface, I start dumping the sand here, and if I make a dump a very great height, then ultimately this dump cannot be vertical. So, this dump will have a slope, and that slope actually natural slope, which will be this beta will be equal to phi. Okay. So, that means it is if I put this a small weight here, again this will collapse, because this is a very limiting condition. So, factor of safety is 1, means it will be phi equal to beta. Okay. So, this is a very simple thing we have considered. We assume that a slope, and we have considered a small mass on the slope, and I considered the equilibrium of it, and from there actually I have tried to equate the forces, and with the requirement of factor of safety equal to greater than 1, and then ultimately I get this expression, and from there if you take F equal to 1, then I get phi equal to beta. That means, if I want to, if I take sand from somewhere, you will see everywhere that truck loaded sand will be coming, and then it will be unloading on the roadside, and you will see sand will be at a particular slope. It will not be vertical, it will not be totally flat. So, that actually the angle comes from here, actually whatever angle of shearing resistance the soil has, based on that it will make the angle. So, this is the first example or analysis of factor of safety, and we will go little complicated slowly. Now, let us take the from here actually you can make a few important observation. You can see that from this it is seen that the weight of a material does not affect the stability of the slope. So, finally, what is the weight, whether it is a if it is a friction is there, whether it is a made of steel, quartz or anything, if the friction is the concept is same, then it does not matter, only it depends on only your the phi, the angle of internal action angle or angle of shearing resistance. No actually weight of the material is not there at all. The shape angle for the slope is the same whether the soil is dry or submerged. That means, I have not considered whether it is a dry soil or submerged soil or partially submerged soil, nothing I have considered. Simply I have considered the weight, and only assumption is that it must be homogeneous, because when I consider a slope and taking a small mass from here, that entire slope region should be homogeneous, the same, whatever soil type here, whatever all should be everywhere, it should be same, then only that is valid. So, this is homogeneous is assumed, but the whether the soil is dry or submerged, that condition actually we have not considered, and that means it is not dependent on it. And the embankment can be of any height. That means, whether this slope is there, it is called infinite slope. That means, whether this slope is 10 meter or whether it is 20 meter, if as far as this angle is constant, whether it is 10 meter or 20 meter or 30 meter or 100 meter, the analysis is same. That means, factor of safety will be tan phi by tan beta. Similarly, failure of a submerged sand slope can occur, however, if the water level of the retained water falls rapidly. That means, it was suppose submerged initially and then suddenly water dropped at this level. Then of course, analysis totally will change and it may fail, and so the water table has gone, but some water is retained in this, and to come out water from the retained soil, that takes some time. So, that lags, because of that sometimes this slope will fail. So, since the seepage forces are set up in this situation, so the failure may occur. So, that means, if it is a submerged, the analysis is same, but submerged but suddenly dropped, in that case analysis will be different. So, how different we will take one by one. So, let us take next slide. This is actually the seepage force in granulation subject to rapid drawdown. That means, we are now considering introducing seepage, and you can see in the next figure I will go. Let me go to the next figure. First of all, I will show how we are doing. So, this is the slope suppose, and when water table is here, the natural phreatic line or groundwater table will be initially will be like this only. Okay. So, it will be like this, and so now if I on this slope, if I consider a mass like previously, then it will have pore water pressure. So, in this there are number of things are shown. I have taken width of this slice, and you have taken height of this slice, base length, everything is defined, and this angle is suppose beta. This angle is beta. So, if it is there, and at the midpoint of this, suppose there is a pore pressure equal to u. If that is the case, then one by one let me go back to the previous one, and you can see as shown in the figure which I have already shown, water level of the river has dropped suddenly due to tidal effects. The permeability of the soil in the slope is such that the water in it cannot follow the water level changes as rapidly as the river. River water drawn down quickly, but inside the soil it could not come out, with the result that seepage occurs from the high water level in the slope to the water to the lower water level of the river. That means, I will come back to the next once again river, and a flow net can be drawn for this condition, and the excess hydraulic head for any point within the slope can be determined. That means, when water is flowing through the soil, that hydraulic head actually that cause excess hydraulic head is causing that actually we have considered while seepage forces. We have seepage and permeability discussed. Then when flow taking place, then through the soil upward direction, downward direction, then accordingly seepage force will be there. So, we have considered. So, similar to that here also, since water table has gone down, but water still retained in the soil. So, water will flow through the soil and towards the groundwater table, and because of that there will be seepage force will act. So, if that happens, then that is the diagram actually. So, this is the flow line, and then equipotential line I can draw like this, and then typically one slice I can take, and this slice geometry of the slice shown here, and based on this we can do some analysis, like you can see the potential failure plane. This is the potential failure plane. Suppose this is the angle beta, and parallel to the slope surface, that is this is the failure plane actually parallel suppose this is not drawn properly. So, otherwise this should have been little flatter actually parallel to this, and occurs at a depth z. That means, from the midpoint to the midpoint is depth z, and element with the slope of weight w, this weight of this is w. Let the excess pore water pressure induced by seepage be u at the midpoint. So, here because of this flow everywhere seepage pressure will be different, and this is suppose you have considered a small element. and in that element what is the pore pressure, and suppose at this is a failure plane. So, we are considering at this point failure pressure is u. So, based on that we can do the analysis now. That means, when there is a flow taking place within the soil. So, if that flow take place, then how the analysis change, let us see that. So, you can see now when normal reaction n like that, it will be W cos beta, and normal stress will be normal force divided by area, and you can see normal force was W cos beta and length was L, that we have shown before, that is it was here and it is like this, and we have taken this as a length L, okay, and this is B actually. So, if I consider if I put L in terms of B, width of the slice, then the L will be B by cos beta. So, if I substitute here, then sigma become W cos square beta by B. Similarly, normal effective stress we can find out, sigma dash will be W cos square beta by B, and minus at that point, suppose this is the point we have considered, this is the sigma, and at this point pore pressure is u. So, effective will be total minus u. So, that if I substitute W equal to gamma z B cos square beta by B minus u. So, this will be the your final expression for this B get cancelled. So, gamma z cos square beta minus B minus u is the normal effective stress at this point. Similarly, if I shear stress you have to calculate. So, you can go back to this, you can see the tangential force is W sin beta, and tangential stress again the load by area, and L again to be substituted, then it will be gamma z sin beta cos beta, okay. And so, this is the tangential shear stress. So, ultimate shear strength will be sigma dash tan phi equal to tau into F, where F is this is the shear strength of the soil and F is the factor of safety, that should be equal to this. And so, we have already calculated horizontal stress is this, and we have already calculated this as a effective stress, and then multiplied by tan phi, that will be effective shear stress, and divided by factor of safety must be equal to the horizontal stress. This is the original factor of safety or stability requirement. This is the equation we have used at the beginning. Similar way, if I use this, then your factor of safety equation reduces to cos beta by sin beta minus u by gamma z sin beta cos beta into tan phi, and if I simplify further, 1 minus u by gamma z cos square beta tan phi by tan beta, and equal to F multiplied by 1 minus R u by cos square beta. So, tan phi by tan beta. You can see when it was a dry slope or submerged slope, if the water table is here or water table is here, if it is here it is a dry, if it is here it is a submerged. In that case, you had a factor of safety of equal to this, and now because of this, at any point, suppose pore pressure is u, and when pore pressure is there, then your factor of safety equation modified to 1 minus R by cos square beta. So, if I know the RU that is pore pressure ratio and the angle, then you can calculate this multiplied by original factor of safety become the factor of safety of this equation. So, since it is always a less than 1 minus something, so this value the factor of safety is reducing. So, it was originally the factor of safety, and this quantity is less than 1. So, that means, because of the pore pressure in the soil, rise of pore pressure in the soil, your factor of safety will be reducing. That means, you have to, that is why when you do the analysis of slope stability analysis, you have to know the condition properly, whether it is dry, whether it is submerged, or whether it is a flowing condition. So, it is a water table is suddenly dropped here and water is flowing in this at particular rate, and if I know the pore pressure development because of that, then I can find out this quantity multiplied the original factor of safety tan phi by tan theta is the new factor of safety. Okay. So, this is the one that is generalized we have considered. Now, let us see one more thing when the flow is taking place parallel to the slope of the. So, this is the one. So, earlier we have considered a phreatic surface initially we have considered a phreatic surface which was a curved one, and now that we are considering the flow is actually parallel to this along this and parallel to this. So, flow is taking place in this direction. In that case, those are flow line. So, we can draw number of perpendicular lines, those can be treated as your equipotential. So, this should be actually parallel, of course, not done properly. This should have been parallel. Okay. These are all parallel, these are all equipotential line, and again with respect to this equipotential line, this beta, and considering the equilibrium of this, we can modify the analysis little, and we can see in the next slide. And you can see if we consider same element as before, the excess pore water head at the center of the base of the element is represented by the height h w, that h w I have shown in the figure, and in the figure A b equal to z cos beta, in the A b cos and h w equal to A b cos beta, and A b equal to z cos beta. So, that means h w equal to z cos square beta, and this one if I substitute, and then the water pressure at the base of the element will be gamma w z cos square beta, gamma w into h. So, if I substitute h, then gamma w z cos square beta will be the pore pressure, and then R u become u by u z. So, if I put this way, then R u become, this is the expression, and if I substitute this expression to the previous slide whatever you have got here, and then simplify, then your this factor of safety will be reduces to this value, that is phi gamma dash by gamma multiplied by tan phi by tan. This is a special case, that means the slope is there, flow is taking place generalized, we have considered u there, and the last case what we have considered, flow is parallel to the sloping surface. Okay. So, that simplifying you the problem, and when you simplify that way, then your expression become gamma submerged by gamma tan phi by tan beta. Gamma submerged, the gamma dash is what? Gamma submerged, gamma minus gamma w, and this is actually total gamma. So, if the soil is having total gamma is 18, so and then your gamma submerged will be 18 minus 9.81, that is water value for water. So, gamma submerged will be this. So, this divided by 18 multiplied by original factor of safety will be the actual factor of safety. So, that is the three different cases, that is purely dry condition or submerged condition factor of safety equal to tan phi by tan beta, and if there is a flowing condition based on u, there is a expression. If there is a third case when there is a flowing condition, but the flow is parallel to the slope, in that case your final expression will be gamma dash by gamma multiplied by tan phi by tan theta. So, this is the three cases I have shown. Next one, there will be a problem given here. A granular soil has a saturated unit weight equal to 18 kilonewton meter and angle of shearing resistance equal 30 degree. The slope is to be made of this material. If the factor of safety is to be 1.25, determine the shape angle of the slope when the slope is dry or submerged and the seepage occurs, and second is if the seepage occurs at and parallel to the surface of the. So, that means, in this problem we are explaining case 1 and case 3, either dry or submerged case 1, and third case is flow is taking place, but it is parallel to the sloping surface. So, in that case you can see the first one you will be having when dry your f equal to tan phi by tan beta, and since the tan beta will be will be tan 30 divided by 1.25. From here I will get beta equal to 24.79 degrees equivalent to 25 degrees. This is very straightforward application. And whereas second case, when it is a flowing taking place and parallel to the sloping surface, then in that case your F equal to gamma submerged by gamma multiplied by tan phi by tan beta. So, if I do that, then your tan beta will be equal to gamma submerged is 18 is the unit weight is given, and water is 9.81 divided by 18 multiplied by tan phi is 30 degrees divided by factor of safety is 1.25. This value will give you beta equal to your say beta equal to, it gives you 11.86. that means it is approximately 12 degrees. So, you can see the requirement when it is a totally dry, I can make a slope of nearly 25 degrees, whereas if because of sudden drawdown condition with the same slope, it can if you keep same 25 degrees, it will definitely fail, because for same factor of safety it is demanding almost half the angle what it was previously. See, it was 25, now it is 12, less than half. So, if there is a tendency of frequent water level going up and down, then you have to make a comparatively flatter slope. You can see the requirement almost less than half. Okay. So, with this application I will stop. I will stop. I will start again maybe with some other cases in the next slide. Thank you.